terminal state here. I've now evaluated all the terminal states, and I know that my opponent's going to choose the minimum of these, right? Based on that, there may be some logic here where I do not have to compute all of these. If I know for a fact that, like 6, I'm never going to possibly get a value of 6 here, because my opponent's always going to choose the lowest value among all 3 of these. So it comes to a point where I know the best possible value I'm going to get is 6. Just scrap it. I don't need to compute it. And I'll show another example of this that's a little bit clearer. This isn't a great example. But based on this, you can actually prune out some of these steps and kill off evaluating their children, because mathematically it just won't be possible to get a better value from it. And so that's the alpha beta pruning. So in this case, you've got a move by your opponent that is, so this move is better for me than this move, but I know I will never actually, or sorry, this move is better than that move. This will never happen because my opponent gets to choose which move it wants to make. And so therefore, I should just cut off anything underneath it. And then the code goes through kind of just how you do this. You basically set a bound for how bad and how good you're going to think you're going to get. So you're working with a range of possible values. So basically, as you're traversing the tree, right, you're going to keep track of what the maximum value is and what the minimum value is. And so when you're in max mode, you can potentially extend this range this way. Or when you're min value, you can possibly extend the range this way. Yes. But if you know that you're not going to ever get it in that direction, you can just stop computing. Right. So if you do some logical tests as you're evaluating these different nodes, and you know, like, I'm at a point where I can't get anything lower than what I've already got, you can just return the minimum and exit out of that particular level of the tree. So let me show you a better example of that real quick. Good old Wikipedia. Okay. We're going to start at our initial node, right? So we're going to start with a blank tree. We're going to navigate down, get down to the terminal state. So at this point, just ignore this. It shouldn't send messages to the terminal. You have 2 possible states for this one here. So you have 5 and 6. Opponent, this is the opponent's turn, so it's going to choose the minimum, so it's choosing 5. Then go back up and you can update this one to also have 5. Go back down to the other children and start evaluating them. You get to a point where you get to 4. And so what you know at this point is, regardless of what other number is chosen by the opponent, so even if this was a smaller number, I'm going to make this decision. The opponent will never choose anything higher than 5, because 5 is set for the minimum already. So it's not going to choose anything smaller than 5. I'm already choosing 5. I know that there's no other choice for it, because 4 has already been populated as a possible minimum. 4 is less than 5. I can avoid calculating this altogether. And similarly, later on in the tree. You guys get that, or you want to go through it again? I understand it's a little complicated. So. And this is the core to the alpha beta pruning, and what you can do to avoid calculating unnecessary states. So I'll try and explain it again. So if when you're traversing the tree, you keep track of what the max and min are for the ranges, you can avoid evaluating any states that are unnecessary. So I've already established at this point, when I get to these child nodes, that the max is 5, right? So the only way that the max could be higher is if at some point for these 3 children nodes, the minimum among these is higher than 5. If I get to a point where I know that the minimum among these is smaller than 5, I can just avoid calculating any more of them, because I'm going to choose 5 for the max when it's my turn. So that happens, the first one's 7, great. That'd be awesome if I could get a 7. Next one's 4. Oh no, 4 is less than 5. So that's what the opponent is going to choose out of these 3. And when it becomes my turn to choose out of the 2 that are available to me, I want to maximize it, I choose the 5. So there's no point in me actually calculating anything beyond the 4, because nothing will ever be lower than 5. Sorry, there's no possible way that the opponent's going to choose anything that's actually equal to or greater than 5. It's already got 4 as an option. So I would choose something lower if there was 2 to 1, let's say, but it doesn't matter. I'm always going to choose 5. Is that a little bit better? I don't know. Okay. Okay. And so basically by building out these trees, you can figure out which is the best move for each opponent and come on up, building it back up from the bottom, you can figure out what is the best move for each player. So it's my turn, I want to make the best move for me, opponent's going to make the best move for them, so on and so forth. One of the problems that I kind of alluded to was that for chess, let's say, the tree is just so massive that there's no way that you could possibly ever get to the bottom. And so in that case, instead of using these terminal states, you could try and use a mathematical function, like we're saying, a heuristic, that could actually act as a terminal state. So you could say, okay, at these spots, I'm only going to go 3 levels down, and then I'm going to use, let's say, for Othello, I'm just going to count the number of pieces that I have versus the number of pieces they have, and that'll be kind of my numeric value for that state, rather than trying to go and compute for an hour just to get all the way down to all possible moves. So this will speed up your runtime. It will actually avoid a lot of extra computation while at the same time still getting good results. It could lead you into problems if you only go down 3 levels and you find out that on the 4th level there's an issue where there was some move you didn't predict because you didn't go further enough down, and you found out that there was a trap played by the opponent and I'm going to lose big time. So you lose that. So you lose the advantage of knowing all that you can about the particular state that you're at and where you could go. But you make up for it by computing faster. So in certain games that have time limits like chess, you need to make an investment within a relatively short period of time. It can't take forever. So you have in that way. Let me go back to the other one real quick. Okay. So that's basically all that I want to go over for project option 2. I'll just take a look at the sample code real quick that I sent you guys. And it kind of lays out that exact same structure that I was going over with the different functions. So you'll see there's 2 different Java files. One is just a data structure that'll help you keep track of a node tree. So it has a couple different values. What the value of the particular node is, what depth it's at, color. In this case, this was for like Othello. It could just be player, but it's a value to show which, what piece, or sorry, what node, who's moving at a particular node. A state is just a 2-dimensional array that keeps the board state. So in the case of tic-tac-toe, it could just be like, you could have like 1 for the X, -1 for O, and 0. It's just a data structure. Or 0 for, no one has gone at that spot yet. So you can just keep track of what the board is. And then a vector to keep track of all the possible children, and a pointer back to the parent node so that you can traverse along this tree. And then just a couple functions. One is the instantiation, where you can set a node, you can set what its parent is, what the current state is, and where it's at. And then 2 different functions, one to add a child and one to delete a child. So basically it's just a simple